Welcome, everybody, to the online seminar series, Machine Learning Needs Mathematical Optimization. We have today the great pleasure of having Gabriel Peire, who is senior researcher at the CNRS and a full professor in the Mathematics and Applications departments of the École Normale Supérieure in Paris. Gabriel is also the Deputy Director of the 3IA Paris Artificial Intelligence Research Institute, as well as a member of the Scientific Committee of the ENS Center for Data Science. He's also the creator of the Numerical Tour of Data Science, which is an online repository for teaching mathematical data sciences. So his work is mainly on applied mathematics and in particular on the imaging sciences and machine learning applications of optimal transport. And the research of Gabriel has been supported by the ERC, so an starting grant as well as consolidator grant. And he has received prestigious prizes from different institutions, so the Academy of Science in France, the Unione Matematica Italiana, and the silver medal from the CRS. And so what can I say? It's really great to have you today. I know that you are very busy, so thank you for making the time. The floor is yours. And for the audience, we function as usual. If you have a very urgent question, put it on the chat and I will read it for Gabriel. And otherwise, we will have time for questions at the end. The floor is yours. Thank you.
Thank you. Thanks a lot, Dolores, for the introduction. It's a pleasure to be here. So yes, of course, if you have questions, you can just stop me anytime. I'll try also to monitor the chat a bit. So if you post question, I will try to answer right away. So yeah, I wanted to take this opportunity to make some kind of a tutorial, I would say, on optimal transports, and particularly speak a bit about like numerical optimal transports and what can you do for machine learning. Maybe a bit of motivation first. I think there is many situations where you actually want to modify or to compare probability distribution in machine learning in general. And this is just a few examples from low dimension on the left to, I would say, higher dimension on the right. On the left, it's mostly like monitoring, for instance, some form of activity for computational neuroscience. You could also think about like image processing problems where you want to modify, for instance, the color of images. Then you could also think about natural language processing application in learning, where the recent trend in the last 5 years or so is to build deep architectures that modify the point clouds that represent text as a distribution of points in a high dimensional embedding space. Then the third example is to represent application in computer vision, let's say, for instance, for generative models for images, where you'd like to model the distribution of images in a huge data set in order to do resampling or to then do more complex downstream tasks for such as classification and so on. And the last example on the right, which is close to my heart, is to indicate application in genomics, so on which I work quite a lot recently, where you do single cell recording. So here it's going to be a distribution of points where each point is basically a cell represented in some embedding space of genes activity, for instance, so a high dimensional space. And once again, you'd like to model the set of cells in order to account, for instance, for differentiation through life, through modification of cells, or also to understand some problematic issues in cancer, for instance, genomics. So, so what do you want to do for all these applications? You typically want to fit some form of a model, let's say alpha that depend on some parameter theta. And the goal is to deform this model in order to represent as correctly as possible some input data sets, here represented as a empirical distribution beta. Okay, and you would typically do this by minimizing some score function or some discrepancy capital D. And basically the take-home message of this talk, one of the, I would say, the most important message, is optimal transports would basically be an automatic way to design this capital D, and it would do so by lifting some what is often called the ground metric little d between pairs of points. So it could be, for instance, the distance in embedding space for NLP, could be some more complex form of discrepancy between images in generative adversarial networks, and could also be in a genomics application, some distance between genes. And what optimal transport will do for you is to take this distance, little d, between pairs of points, so let's say d of xy, and then map it to a distance between arbitrary number of points and more generally distribution. You could also think about having an infinite number of points, in which case you'd get some form of densities. So really optimal transport is really like a lifting mechanism, if you want, between little d and capital D. And the goal of this talk is to discuss how you can do this, because this is quite expensive numerically, and also what are the trade-offs in practice, what do you need to do to have good performances. We'll skip this, so this is a mistake. So first of all, speak a bit about optimal transport that you might have heard of. The initial formulation, which is often called Monge problem, is basically finding a bijection, so a permutation between two groups of points with the same number of points, okay, in order to minimize the total travel distance. And this is a very old problem, and this is also a very difficult problem, because basically the number of permutation is huge. You get an exponential number of such permutation. So basically doing an extensive search is just not possible. So Monge basically raised the question, but he was not able to answer it by an algorithm. Something else that, of course, immediately comes to mind is how do you do if you don't have the same number of points, which in this case, of course, you cannot create a bijection. So these two issues, numerical issues, and I would say modeling issues, basically ask for an extension of this formulation, okay? And the formulation that you should remember, the modern formulation, is not due to Monge, but is due to Kantorovich during the Second World War, which is more general because now you can compare an arbitrary number of points, and basically you can compare arbitrary probability distribution. So in my talk, I will only consider discrete distribution for the ease of simplicity, but you could also think about even like having an infinite number of points. But for the sake of concreteness, I will only consider two groups of points, the xi and the yj, which are equipped with weights ai and bj, which I restrict here to be probability weights, so positive and summing to 1. And the genius of Kantorovich is to describe basically the transportation, not by a bijection, but by what Kantorovich called a transport plan. So for him, the goal of Kantorovich was to really do planification of economy. So his ultimate goal was to formulate a mathematical theory of economy. But in modern terms, in probability, it's often called a coupling. So what is a coupling? It's basically if you get two sets of weights, A and B, an array of number. If you get n element in A and m element in B, it's an array of size n times m, which are positive. And each time you put a non-zero element Pij in this array of number, it means you're going to transfer some mass between Ai and Bj. Okay, so instead of only considering a permutation matrix, you can consider more general coupling. So this is a relaxation. Okay, and then what does it mean to select the optimal coupling, the optimal transports? Then Kantorovich made a very strong hypothesis, a modeling hypothesis, an economic hypothesis, is that the cost of transport should be linear. If you double the mass you transport, you should double the price. Of course, it's a very strong hypothesis, but this is simplifying a lot the problem, because now you simply need to declare what is the cost you pay for a unit amount of mass. And the most usual choice for this is to say this is some power, capital P or small p here, of the distance. So for Monge, it was just p equal 1, but you could consider more general p. And then you simply sum all the possible transported mass, so Pij multiplied by the cost, which is the distance. And subject to the constraints, what are the constraints you need to satisfy? First of all, P needs to be positive. This is obvious. But also you need to satisfy the conservation of mass. You need all the mass from the input A to be distributed. So it means that AI should be equal to the sum on J of Pij. Okay, maybe I can use a pen here. So you see this relationship here. It's very important. It's the conservation of mass on the left-hand side. And then you get the second relationship, which you sum on I. And then you should get back Bj. So then this is conservation of mass. On the other side, you should receive all the mass, okay? So for Monge, it was just a bijection, but here it's more general. And for the rest of the talk, I will simplify this equation by writing them using matrix multiplication, that capital P multiplied by the vector of 1 should be equal to A. And when you multiply by a vector of 1, what you do is simply summing on the row. So it's a bit like a convenient writing style. So then this is very nice because you see that the constraint now becomes simply linear constraint. So you minimize a linear function under linear constraint. And this is basically the birth of linear programming, of modern optimization, if you want. And for the creation or the study of this problem, in fact, Kantorovich got the Nobel Prize in Economy in the 70s because it was a groundbreaking way to model economics using something that is tractable. Because, of course, as you might all know, linear programming is nice because this is a convex optimization problem. Not only it's convex, but it's very nice. And at the same time that Kantorovich basically studied mathematically this program, George Danzig, probably the most famous mathematician in optimization, came up with a simplex algorithm. Sorry. And of course, what is very important is that on this particular case of linear program, then there is some instance of simplex algorithm which run in roughly cubic time complexity. The complexity is basically n cubed log n square. So it means on this particular instance, you can solve quite efficiently actually optimal transport problems. Of course, well, it's depend on how much large n is. N cube is okay if n is of the order of 1,000, but if you want to scale to very large learning application where n can be millions or even larger, you might run into trouble. But it's fair to say that it's really the combination of Kantorovich and Danzig that makes this immensely popular in many, many areas of science. And it's currently, of course, solved routinely in many, many industrial applications. So what's all the fuzz about this? Well, it's nice because you have the transportation, but what is even transportation plan, sorry, capital P, but what is even nicer is if you look at the cost of the optimization problem and you raise it to the power 1 over P here, don't forget this 1 over P to define a proper notion of distance. Because this is going to be a distance, maybe I can just show the whole slides, which is often called the Wasserstein distance. So it's nice, it's a distance. It's 0 if and only if the 2-point cloud are basically equal, if alpha is equal to beta. But you might know lots of other distances, such as, for instance, the total variation distance and other type of let's say, simpler distance. So why should you care about this Wasserstein distance? What is so nice about it? It's basically that it's a nice geometrical distance in some sense. A way to see that it's a geometrical distance is to look at the topology induced by this distance. And it's basically this theorem that at least if you are on a compact domain, if capital X is a compact space, then it's equivalent to the so-called convergence in law in probability. So what does the convergence in law mean? Well, basically this is the definition for the convergence in law. But the meaning is simply that it's a geometrical convergence. It's convergence of all possible expectation. But if you look at what happened for point clouds or weighted point cloud, it simply means that the 2-point cloud become closer and closer together. But of course, since you deal with probability distribution, what could happen is at the limits, if you look at, for instance, these two red points here, in the limit, they are going to fuse to a single point, in which case, of course, the mass of the 2 red points should be equal to the target blue point. So basically, convergence in law means convergence of the support plus, of course, equality of the mass at convergence. So this is a very nice notion of convergence. If you know about the central limit theorem, you know that it's a theorem that is stated according to the convergence in law. So in some sense, the Wasserstein metric is a way to quantify how fast convergence in law occurs. And this is this theorem that tells you that convergence in law is equivalent to convergence in Wasserstein distance. And really to insist why this is a soft or geometrical notion of convergence, you can look at what happened on a single Dirac. So here you get a single Dirac that progressively shifted towards the target destination, little x. So what does it mean for a single Dirac to converge in law, since you need all possible expectation to converge? It's basically that the point itself, xi, converges towards the final destination. And for the Wasserstein, everything is nice because you see you raise the distance to the power p and then to the power 1 over p, which means that if you look here, you see that the Wasserstein distance between two Diracs is just equal to the distance itself, which is what I've told you in the first slide of my talk. Wasserstein is a lifting mechanism. It lifts this little d to capital D, which here is the Wasserstein distance, while satisfying this equality. And you can show that under some mild assumption, this is the only distance that satisfies this property. In sharp contrast, if you look at what happened for the total variation norm, or what is often called the L1 norm between two measures, what happened for the L1 norm, if the 2 Dirac delta xn and delta x are not at the same position, you get a +1 here and a -1 here, so +1 here minus this Dirac. The total variation is always equal to 2 between two Diracs if they are not exactly equal. So you see that the total variation distance, which is arguably the simplest distance between probability distribution, is not converging to 0. So you see here there is a very strong distinction between these two notions of distance. Total variation is a non-geometrical distance, but it's very simple. Wasserstein is a geometrical distance, but it's harder to compute. It's more or less the second take-home message. If you want a geometrical notion of convergence, you need to pay some price. You need to solve some optimization problem here. And this is what we are going to discuss next. Okay, so let's say the Wasserstein distance has nice property, but you need to pay some price for it. So what are the trade-offs? First of all, the algorithm, if you want exact precision, are slow. Okay, the algorithm is roughly speaking up to logarithmic term cubic, whereas the total variation is linear time complexity. The other issue that I want to discuss is the curse of dimensionality. If you want to compare optimal transport between two distributions, one of which being like, for instance, a Gaussian or some kind of continuous densities, you can show that the number of points will grow exponentially with the dimension. Okay, so even if d is like 10, the number of points you would need to discretize the problem would be enormous. And the way to cure this problem that I would explain to you is called entropic regularization. It's very nice, very simple. It leads to faster algorithm, and also it's able to somehow make the algorithm scales better. The other thing that I want to discuss, and that we would say it's quite easy actually to cure or to fight, is the lack of stability of optimal transport. If you get some outliers, for instance, here you see these 2 points, which are like clearly outlier out of the data set, optimal transport will be very sensitive to this outlier because it will need to send some mass to the outlier, and it's going to be very problematic for some application, in particular in biology. And the way to cure these outliers, and I will explain this, is to introduce some weak notion of optimal transport, some relaxed notion that accounts for unbalancedness in your data, and we have studied this in details, and this is called unbalanced optimal transports. And the last thing that I want to discuss, and I will probably not have time to discuss in detail, but I will give you some indication for this, is how can you do optimal transport between two spaces? And this is very, very important in some applications, for instance, in biology, where the cells comes from two different types of modalities. Let's say here, it's an RNA-seq, where the data belongs to the space of genes, and on the left, it's called ATAC-seq. It's another type of sequencing, for instance, device, where the data belongs to some space, which is called the space of peaks, and that have a lower dimension. Can you still do optimal transport? And it turned out that you can, but you need some serious work, some serious non-trivial extension, which is called Gromov-Wasserstein, that I would try to illustrate. Okay, so you see, this is more and more advanced. The first thing is just like some simple algorithm that I want you to know. Then the other is like some I would say extension of it. And the last one is some much more advanced and non-trivial extension for which there is still a lot of questions. And I like questions. It's nice to have open problems. So let's speak a bit about like the first thing that is probably the most important that you should know about. It's called entropic regularization, but actually it's something very old that is known in statistical physics as Schrödinger problems, because basically it's Schrödinger that invented this. So it's not quantum mechanics Schrödinger, it's statistical physics Schrödinger. And it's in fact older than Kantorovich, which is quite nice because it shows you that we are like somehow going back in time. And the idea, the question of Schrödinger, which was not at all for data science, is like some kind of abstract problems. Imagine you have two sets of molecules of gas, the Xi and the Yj, and you just know two snapshots of the gas at two different times. And now you ask the question, what are the most likely trajectory or transport, according to Kantorovich, between the molecules of gas? But now there is a key distinction with respect to Kantorovich, is that molecules of gas do not travel in straight line. They are not deterministic. They are Brownian motions. So you need to introduce the temperature of the gas, which here is epsilon, to model the stochasticity of the problem. And in a very nice paper in the 30s, Schrödinger did all the mathematics derivation about the equation that needs to be satisfied by the maximum likelihood estimator of how likely are two molecules of gas to be connected by a Brownian motion. So don't ask me for this because it's kind of a very hardcore statistical physics. But if you look at the final equation, it's beautiful because the most likely connection, Pij, is just solving Kantorovich problem plus epsilon times the negative entropy of the coupling. So you just take Kantorovich problems and you penalize it with epsilon Pij log of Pij. And according to Schrödinger, you solve these long-standing problems of statistical physics. So really you see what's happening as epsilon goes to 0. The molecules become more and more lazy. So it's what Schrödinger called the lazy gas experiment, and then you recover Kantorovich problems. I think a nice way to see what's happening is to do numerical simulation. So I will explain after how do you do the numerics. What you can prove is as soon as epsilon is strictly positive, in fact, Pij is strictly positive everywhere. So you get tons of connection. Everybody's connected to everyone. So to be able to see something interesting, what I'm displaying here is only the Pij that are larger than 10 to the minus 3. So in some sense, connections that are strong enough. If epsilon goes to 0, this is actually another very famous theorem. It's a theorem by Birkhoff and Feynman in 55, 53, that tells you that as epsilon goes to 0, Kantorovich problem is actually going to be a solution of Monge problem. So you're going to have actually a bijection, so a very, very sparse set of solutions. But you see what happens as epsilon increases, the most likely connection, according to Schrödinger, are going to be more and more dense. So you're going to have more and more connection. And in fact, you can show that as epsilon goes to plus infinity, you're going to basically connect everyone to everyone. So this has two very important and major implications for us. The first thing that I will explain just after is the algorithm will be faster and faster. Having more connection, maybe this is not so intuitive, will lead to faster algorithm. So this is somehow a nice thing. The other things, which is very important from, I would say, machine learning perspective, is as epsilon increases, you get more and more stability. You get more and more connection, so the solution would become stable and stable. So the output of this stability would be that in high dimension, you would need less points to have accurate estimation, which means that somehow you would be able to fight the curse of dimensionality. So really the take-home message that I will explain in the following slide is you're winning on both sides. By increasing epsilon, you become less sensitive in high dimension, so you depend less on the dimension, and at the same time you get faster algorithm. So basically, instead of cubic time complexity, you would simply have basically quadratic or even smaller complexity. So this is why I like a lot this algorithm. What is this algorithm? Basically, the most important slide of my talk, because I love this algorithm so much. It's my probably favorite algorithm of all time, with probably the fast Fourier transform or some other iconic algorithm. It's not so well known, but maybe you've heard it from time to time because it appears in many areas because it's linked to other problems. This algorithm, I like to call it SYNCHRON, but it has many other names, such as iterative fitting procedure, EPFP. SYNCHRON is basically the mathematician. He's not the one that invented the algorithm, but he's a mathematician that studied the theory of this algorithm. So this is why also I like to call it SYNCHRON. In honor of SYNCHRON, which is not so well known, but is probably a very important mathematician of the previous century. And this algorithm turned out to be quite simple. How do you basically come up with this algorithm? You get this optimization problem here, for which you get two constraints, this constraint here and this constraint here. So what do you do immediately when you have a constraint optimization problem? You introduce Lagrange multiplier. So you basically have two Lagrange multiplier, U and V. And if you write down Lagrange theorem for this, you discover immediately a very nice property, is that you are solution if and only if, of course, you satisfy the constraint here, but at the same time, you should be able to write your solution in so-called Gibbs exponential format. So if you know about statistical estimators that you cook up using maximum entropy method, this is exactly the same theory. This is just maximum entropy applied to optimal transport. What does the maximum entropy principle tell you? Is that your solution, capital P, should be factorizable using a Gibbs kernel. Okay, and here this is the definition of the Gibbs kernel here. Capital K is your Gibbs kernel. It's basically, it's very simple. It's just exponential minus the cost divided by epsilon. So think about the cost being Euclidean and P equal 2. This is a Gaussian matrix. So K is fixed. It's just an enormous Gaussian matrix. What you need to do is to be able to multiply the rows by Ui and the column by Vj. This is often called a scaling format. You should be able to scale your capital K such that it satisfies the sum constraint on the rows and the column. Let's take an even simpler example. Let's take A equal 1, okay, and B equal 1. So uniform distribution on 2-point cloud. What you are asking for is, can you scale a positive matrix, a positive kernel capital K, so that it becomes bistochastics? And this is actually a very, very important problem, probably even more important than optimal transport. Why would you? So Ui is just a scalar. So this is just a scalar number. Okay. So these two guys here are basically scalars. But here I store them as two vectors. I'm not sure why you, so Ui is just a scalar, so you don't need to transpose it. After I would put transposed, but this would be when I consider vectors and matrices. But at this level, this is just for each entries ij, you multiply kij by two scalars. Another way to look at this, I'm not sure this is so helpful, but this is to rewrite, I mean, for me it's helpful because it's more compact, is to rewrite this equation in this format. And this is usually why people call this diagonal scaling. You multiply k by a diagonal of u on the left and a diagonal of v on the right. So the question if A and B are 1 is, can you always scale a positive matrix so that it becomes bistochastic? And the very nice thing here is, because this problem here is strictly convex, it has a solution first, and this solution is unique. So here, this very simple Lagrange equivalence tells you that you can always scale a matrix toward bistochasticity. And this solution, there is a unique scale matrix, which is maybe not so surprising, but it's nice to have a two-line proof of this implication. Now the question, the interesting question is, how do you find the U and the V in practice? And I think there is a very nice heuristic to find this, is to simply look to rewrite this in this matrix format first, because it's simpler, and to simply multiply on the right this matrix by a vector of 1. Okay, if you multiply this matrix by a vector of 1, you get this equation here. You multiply diagonal V by 1, you get basically just V. Okay, and now if you see what does it mean to multiply diag of U by this vector, it's simply U multiplied by KV. And here, this application is just the Hadamard product. Okay, Hadamard product is simply multiplication of two vectors, entries by entries. So to summarize these very simple findings, is being a solution of Schrödinger problem, so we say an approximate solution to optimal transport, is as simple as solving two equations here in U and V. Because of course I've done the first equation, but the other equation is the same, simply you exchange the role of U and V. And here you put a transpose. Okay? So solving optimal transport approximately is as simple as solving two equations with two unknowns in U and V. And these two equations are just polynomials of degree 2, because this is just a bilinear equation in U and V. But of course, it's not so simple because the dimension is huge. So it's just a polynomial equation, order 2 polynomial equation, but in dimension that might be 1 million or so. So this is both good and bad. But the nice thing is this first equation is very simple if you view it as an equation in U. And this equation is also very simple if you view it as an equation in V. So how do you do in practice to solve this equation? I mean, the heuristics is simply, well, give me a tentative solution for V, like an initialization, then I can compute the optimal U very easily by simply solving this equation by dividing A by KV. And here, be careful when I say division, it's once again Hadamard division, entry by entry division. Then I can compute the optimal U, but then the V is not optimal. So of course, what I do is I solve for V, okay? And then it's like a chicken and egg problem. So what do? Well, you do a fixed point. You iterate on U and V, etc. And basically you cross your finger and you hope it converges. question, does it converge? It's not so easy to prove. I mean, when you know the solution, it's very easy, but as usual, the question is how do you prove it? And it was proved by Synchron here in 64. And what I like a lot about the proof of Synchron is that it's beautiful, it's very nice, especially if you know about Markov chain. So if you know about Markov chain, the proof of Synchron is just the same proof, which is called basically Perron-Frobenius theorems. And how do you prove Perron-Frobenius theorem, a quantitative version of Perron-Frobenius? You use contractance of the multiplication by a matrix, a positive matrix and a vector, according to a metric which is often called the Hilbert metric. So I won't go into the details, but basically the proof of Synchron is exactly the same line by line as the proof of Perron-Frobenius by Birkhoff, who proved contractance. So it's not hard once you know this. If you don't know about Birkhoff theorem, then it's a bit harder. So the good news, it converges. The other good news, it converges very fast if epsilon is large, because when you look at the proof, you immediately see that the convergence ratio will become very, very small as epsilon increases. So it's really like, okay, it's both positive and negative. This is an algorithm that goes very fast if epsilon is not too small. If epsilon is small, there is no workaround. You should use a simplex algorithm. It's going to be much better. So for large-scale problem, the take-home message is don't use this with a small epsilon, otherwise it would take forever. Well, you can do more mathematics. I would spare you the details. We wrote a fair share of papers about this. And for instance, if you really are looking for refined complexity results, if you want some precision on the solution, let's say on the cost, on the optimal transport cost, then you can show that you should select epsilon roughly equal or proportional to the precision you want on the optimal transport distance. And in this case, you can also show that the number of iterations would be of the order of 1 epsilon square. Okay, so the complexity, if you want to use it for optimal transport approximation, is going to be n squared divided by epsilon square. So here, once again, you see the glass half empty or half full. If you want high precision, epsilon is going to be small, and this is going to be catastrophic. Okay, because 1 over epsilon square is very bad. Okay, if you do interior point would have a complexity which scales, roughly speaking, like log n divided by log over 1 epsilon. Okay, so you see that interior point have a much better dependency according to epsilon, but the worst dependency according to n. Okay, but this is only if you want to approximate optimal transport. And what I would explain later is in practice, in high dimension, you might actually not want to approximate too accurately optimal transport. So in practice, it's not even clear that you want epsilon to be small. Okay, but okay, the rule of thumb is don't use epsilon too small, and this algorithm is fantastic. It's fantastic because it's very simple also. I mean, this is an algorithm that is basically 2 lines of Python code. It's very simple to implement. So it's really, really a game changer. The other thing that is super important in practice is that this is an algorithm that is very easy to parallelize on GPUs. So if you want to use it for deep learning application, where Synchron would be used to train deep architecture, this is really a game changer, because you see that the only bottleneck in terms of computation is multiplication by a matrix, which is something that is very nicely handled by GPUs. So I would say that on top of this, one reason why people use Synchron in machine learning more than any other competing algorithm is that it's something that is extremely nicely parallelizable on GPU. So you see like everything like is aligned for usage on machine learning application. Okay, so now I come to maybe something that also is very important for me, is what happened in high dimension, because many, I would say, mathematicians working on optimal transport, they would say for you, like, the dimension is just a constant. And this is a constant and we don't care about it. But for machine learning application, the dimension is not a constant, or at least it is the most important constant. So you should always say how much your theorems depend on the dimension. And the answer, or at least what will happen in practice, or in many cases, is that the dependency would be horrible. I won't lie to you, this is not a good news. So let's look at probably the simplest question ever, is what is the number of samples you need if you want to discretize optimal transport? I'm not even speaking about solving a complex task. I'm just saying, can you even dare to compute the Wasserstein distance between 2 distributions? Let's take a concrete example. Let's take alpha, for instance, a fixed point cloud. But let's think that you want to match alpha to some continuous densities. Might be a mixture of Gaussian, might be a more complex deep learning models, but it's like a continuous density. How many samples do you need to draw so that the Wasserstein distance between your unknown, I would say, model, so this is like your target, is matched by this approximate computation in finite dimension. And on average, for instance, on replication. So here, I'm assuming the dots here are drawn independently from each other from beta. And the bad news, according to, for instance, Richard Dudley in the 60s, and this has been refined immensely over the years, so this is the most simplest theorems in Euclidean space, is that the number of samples you need, unfortunately, grows like 1 over the precision to the power of the dimension. And I think this is really the definition of the curse of dimensionality. When you get this type of exponential dependency, this is what people would call in statistics curse of dimensionality. So this is the bad news. Now what we've been working on over the last few years, in particular in the PhD thesis of Ojenve, is to study these problems not for optimal transport, but for the cost of synchron. So this is like this epsilon here. When epsilon is 0, is going to be the optimal transport. So this corresponds to setting epsilon to 0. And when you increase epsilon, then you get synchron cost, which is a bit different from it. And the intuition is because you gain stability, you become immune to the dimension. This is what Aude proved. She proved that as soon as epsilon is strictly positive, you get what is often called a non-parametric rate, which is the fact that the number of samples is 1 over delta to the power 2. Has the best rate you could imagine, because this is typically the rate you have with Monte Carlo methods. So in some sense, if you think about Monte Carlo method to estimate integral, this is roughly the same situation here, except it's more complicated. This is not an integral, it's an optimization problem, but it's the same idea. But this is, I would say, the bad news, but the good news, sorry. But the bad news is, unfortunately, of course, the dimension which starts to kick in as epsilon decrease, and you see it in the dependency in the constant. So this is, of course, the constant. So if I were, let's say, a theoretician, I would say, okay, it's just a constant, we don't care about it. But in fact, you see that as the dimension increase, this is bad, because if you want a high precision, a small epsilon here, you would need, of course, a number of samples that would grow immensely. So you really see the trade-off is if you don't care about approximating too much optimal transport, this is a good news. You can do this in high dimension. But as soon as you would start to want to reach high precision, so to decay the value of epsilon, you would start seeing the dimension appearing. And this is, in fact, a no-free lunch result, because, in fact, this theorem of Dudley, not only it's an upper bound, so you can show that this requires this number of samples, but there is also a matching lower bound. This means that for any possible algorithm, you can never improve over this rate, even if this is a Gaussian distribution. So even for a very simple distribution, you need this number of samples. Okay, so if you want to be smart and use synchron to actually solve the initial problem of Dudley, you would need epsilon to decay with n, and then you would face once again the curse of dimension. So really the take-home message is synchron is not a way to cure optimal transport from the curse of dimensionality. It's a way to say maybe optimal transport is not so important. Maybe actually things would work fine even with not so small epsilon. And then the theorem of Aude is telling you that yes, you can do this in high dimension. Finally, this is only the start of the story, because the question is, what can you do with this W epsilon? Can you solve practical problem? And I think this is still what is missing in the theory, not only for us, but for other methods. There are other methods than optimal transport to match distribution, but nobody has any real theorem that says, with this, I can solve accurately this or this machine learning problem. And this is really something that theoreticians should focus in the future. But I would say, okay, this goes in the correct direction of telling you, you can have something that looks like optimal transport, but at the same time that you can estimate in high dimension. What can you do more on top of this? And I would like to spend some time to conclude on this. What can you do in practice to make this even works better? So I would speak mostly about the first aspect, unbalanced optimal transport. For those who are interested in the last aspect, Gromov-Wasserstein, I would quickly skip about it. And if you want, we can discuss after, or you can send me emails. Also, the slides are online, so you could have a look at the slides. But for me, what is more important, I would say, is this slide on unbalanced optimal transport, because it's something that people are facing in practice. And I often receive mails of people that are like disappointing about optimal transport, but basically because they are not doing this. One key issue about optimal transport is what happens if you get outliers. More generally, what happens if the two input distribution doesn't have exactly the same mass, if they are not like probability distribution. And the key problem with optimal transport, what makes this not working well in many situations, is in optimal transport, you really want exact equality between the first marginal p times 1 and a. And the same, of course, for b here. And this is what is problematic, is the exact conservation of mass. So what we have been proposed with a collaborator, including the PhD thesis of Lena Shiza, and this is actually also something that was developed by a few mathematicians, including Liero, Milke, and Savary at the same time. This is exactly the same contribution. Also, I should credit Leonard Monsainjon in Portugal, who give also a very similar definition, is if you want to do things that are a bit better behaved, you should not ask for P1 equal exactly to A. You should simply ask for this to be approximately equal. And a way to do this is, instead of imposing exact equality, is to penalize, to do like a soft penalty. Okay? And here, this penalty, there's many ways to formulate this penalty, but the best situation and the best mathematical property occurs if you measure the discrepancy according to the relative entropy, which is often called the Kullback-Leibler divergence. Okay, so for those who don't know what is the Kullback-Leibler divergence, this is just some kind of distance between two probability distributions that is basically just a derivative or a related quantity of the entropy, of the Shannon entropy. Okay, so this is just measuring how much the marginal is equal to A. And here you see, maybe I can take another color, is that there is a parameter tau here that you can select. If tau is very large, then you recover classical optimal transport. You recover that you exactly want P1 equal A. But if you decrease the value of tau, then you would get more and more relaxed formulation, and you would allow for more variation, so more robustness to outlier. Okay, and here on the other part of the slide here, it's a numerical experiment on a very simple scenario to show to you what's happening with this relaxation. So here what I do is I want to transport together two mixtures of Gaussian. The red here, that is here. Okay, you see the first mixtures. I want to match this mixture with another mixture, which is the blue one. But I've been a bit tricky to model a bit what's happening in practice. You see that here, I've put a little bit of mass on extra. Okay, so that optimal transport is not allowed to transfer this mass here to this one because there is a bit too much mass. Okay, so basically what optimal transport has to do, it has to transfer a bit of mass to the second Gaussian here because the second Gaussian has a bit too much mass. Maybe it's okay for you, but I think it's not so nice that you have to send mass very, very far away. And you can clearly see this in the optimal transport coupling capital P. You see that the shape of this optimal transport coupling here is very bad. You get a local transport here. Okay, it's fine. It means you transfer a bit of mass locally, but you get also a bit of mass that is transported to the other side. Okay, so you see that the shape of the optimal transport is very, very irregular. It's like there is a split of mass. And this is not acceptable for most applications because it means that the transport is very irregular. What I find to be very nice is as soon as you decay a bit the value of tau, you allow for a bit of unbalanced situation, you recover a local transport. And it is what is indicated here and here. You see that the non-local part has been totally removed. Here, you have removed the teleportation of mass. Okay, and what has happened, if you want, another way to interpret this, is by relaxing a bit the marginal constraints. Here I display on red this is P times 1, and in blue it's P transpose times 1. So it's what is actually transported by the algorithm or by the solution. And you see what's happening. Here you have killed a bit of mass, and then here you have created a bit of mass. But you've done this automatically. Of course, you could have said this from the start. You could have said, okay, here I have a little bit of mass on extra. Here I lack a little bit of mass. Okay, let's do some adjustments. But this is simple in 1D, but in high dimensions, it's not possible. Here, the algorithm does this automatically for you. It automatically adjusts all, if you want, local modes in order so that they have the correct matching of masses. And this is so nice. I mean, honestly, I find this like a bit of magic. But there's no magic. It's just like just the effect of regularization. Then you could say, okay, what's happened if you remove too much mass? It still works. So if you decay the value of tau, but it starts having some pollution. And there's no real theory for this, to be honest. But you see what's happened here is if you look closely at what happened, you see here the local maximum has shifted a bit on the left here and a bit on the right here. It's not so dramatic, but it gives you a less accurate estimation of optimal transport. And you see like this is like this effect of this little like deviation. And if you start like being a bit too greedy, destroying a bit too much of mass, then it starts to be a disaster. So I would say, roughly speaking, and it's not a theorem, there is a sweet spot. And here the sweet spot is basically on this area between, let's say, 0.1 and 1. You get the correct amount of creation and destruction so that you get a very accurate estimation of the actual transportation. But once again, there's no real theory, but it kind of explains what happened in practice. If you get real data set, you always get some noise, some outliers. By adjusting this value of tau, you might automatically the algorithm adjust for these errors. Of course, in practice, there is no like a magic recipes. You need to do some kind of fine tuning for the value of tau. If you do machine learning, you should do cross validation. It's a typical scenario. But I can assure you that in practice, this is kind of a game changer. So, well, if you want to deploy optimal transport for real life application, I think you should do something like this. I mean, maybe not exactly this, but at least to to be immune to noise. This is the first, thing. This is it. If you want to have some theoretical results, I don't want to speak too much about it, but those who want to know about this, they are welcome to join, to contact me or to read the paper, basically, where we show that it still define the distance, and with some little adjustment for the cost, it's going to be actually a geodesic distance. The second thing I want to mention is that there is actually a very simple modification of Synchron algorithm that is able to cope with unbalanced optimal transport. And the modification is really minor. So let's ignore the gamma here. The gamma is to account for more general cost. Let's just take power P, for instance. In this case, this would just be like power P. This would be exactly the previous Synchron algorithm. And I spare you the details, but you can do exactly the same derivation as before, introducing Lagrange multiplier for these two terms, basically. And you would see that you get exactly synchronous iteration up to a very minor modification, which is that you need to raise the iteration to some power. And you see this power is strictly smaller than 1. And if you let tau goes to plus infinity, then this would go to 1. Okay? If you let tau be very large, this is to be expected, you would recover classical optimal transport and recover classical synchron. So the only effect of this is by raising to some power smaller than 1, it would basically shrink the multiplier and leads to modification of the conservation of mass. So it's like very small modification in your code. One typical application that I like a lot, because I work quite extensively nowadays in genomics, is a nice paper by Shibinger, which is like a computational incarnation of a very old theory of Waddington in the 30s that was looking for how cells evolved during life. So basically, the first days of evolution of an organism, here it's for mice, how would cells evolve? And there was a conjecture by Waddington that they evolve according to some landscape. And the landscape is a very high dimensional landscape, and nobody really knows what it is. And here what they did, Shibinger, is actually recording cells at different days. So this is like day 1, day 2, day 3, and so on. And this is like evolution. And here's just a 2D display, but it's actually a very high dimensional set of cells that has been recorded by the technologies of RNA sequencing. And what they do now, the question they ask is exactly the question of Schrödinger. So it's a bit like Schrödinger in practice. They ask, okay, you get this snapshot of cells at different time, but since every time you do the recording, the biopsy, you destroy the cells. So when you move from day 1, from day 2, you have 2 different biopsies. So you lose track of the trajectories. And now what you can do, and what they propose in these quite highly cited papers, is to do unbalanced optimal transport to recover the bijection. Okay, by solving the optimal transport, you can recover the bijection, and you can basically say that these cells, which initially you don't know what it is going to evolve to these cells, which if you know a bit of biology, you know it's going to be like a T cells or a B cells or whatever. So it's really a huge breakthrough in biology. So it's nice. It's nice. I think I'm running out of time. So I will basically skip the last section on Gromov-Wasserstein. If you want just a teaser, the question is how to do optimal transport between two different spaces. And the answer is very hard, but you can do this by solving a non-convex optimization problem. This is the functional you want to solve, which was introduced a few years ago, almost 10 years ago, by Facundo Memoli and Cartol Sturm at the same time. The difficulty is that this is non-convex, and this is even more than non-convex. It's actually NP-hard. And it's linked to quadratic assignment problem for those who knows about quadratic assignments. So I would not tell you much about this because we don't know much about this. We don't know anything about the theory. Basically, and I would skip this these things. I would just show you some nice application at the end. You can use some kind of heuristic algorithm based on synchron, okay, which is like quite nice, but there is no theory for this algorithm. Okay, what are the applications? Maybe I can show you some nice application in this very recent paper. I think one of the most exciting application is once again in genomics application, where you want to recover connection. It's not connection in time. Now it's connection between two different spaces because you do recording in two different modalities. Let's say RNA and ATAC, which are two different modalities. And now you know they come from the same living organism. So you know that this cell, roughly speaking, should be somewhere like around here, but you don't know exactly where. And you'd like to fuse the two data sets together. Another application, which is called NovoSpark, has been introduced recently, is also if you want to, you have data set in space of genes, but also you have data set in terms of images. You've taken some snapshots, some images of the brain, and you know that cell should be located somewhere. And here, once again, you'd like to make the connection. And you like to do this by optimal transport. And this paper proposed to do this by solving a Gromov-Wasserstein problems. And they have some very nice results, some nice evaluation, and it seems to be quite promising. But once again, there is absolutely no theory for this. So, and okay, to just tell you what we've been doing recently, we have been adding this to the unbalanced problems. So I would not describe this, but if you're interested, feel free to drop me an email. And this is a nice recent result by Othman, who is a PhD student with us, that did some nice application to genomics, the same application as before that I've told you between RNA and ATAC, which is a very challenging application. Okay, so just some conclusion, and I'd like to conclude basically by open problems. I don't want to recap what I've said because, as you notice, optimal transport is great. What are missing nowadays? I think what is missing is understanding better this entropic regularization, this epsilon. Why does it work with epsilon not so small, is not so well understood, and I really like to understand better for real application what you can say. Now for the other application in genomics, what is still lacking is the theory. We don't have theory. We don't know about basically whether solution to this problem. Do they lead to bijection? So what is called Monge-map. This is totally not known. And when epsilon is not so small, or even if epsilon is small, can you connect the Schrödinger problem to the limit problem is not so clear. So I think this is very exciting for mathematicians. It's a very exciting time for mathematicians because there's many open questions, and also for practitioners to design even faster algorithms. So sorry for being a bit late, but I'd like to hear your question if you have. Don't hesitate to ask as many questions as you want.
And remember, if you have questions, please raise your hand and we will give you the rights to the microphone and the camera. Thank you very much, Gabriel, for this very interesting presentation and also for the open problems. So is there any questions from the audience?
Don't be shy.
So Emmanuel has a question. So Yasone, if you could give the rights.
Thank you very much, Gabriel, for this great talk. Again, you make me, this is already the second time that you made me feel like jumping immediately on the optimal transport community and try to contribute. I have a question regarding the Gromov-Wasserschein problem,
Okay.
the last one you showed us. So the difficulty comes because of the bilinear terms, no?
Yes. Yes.
But it still is has a lot of structure there. It's not a generic convex quadratic problem, right?
Yes. Yes.
Trains are still linear.
Yeah, so this is actually very interesting. I totally agree with you that it's not a generic non-convex problem. So maybe if you want, I can say a few words about this. So first of all, so maybe a simple situation that is very important in practice, like for genomics, is the case of Euclidean space. And if the space are Euclidean, you can actually show that it's a concave function. So basically, you are minimizing a concave function on
a
this
polytope, which
transportation
can be very demanding, of course.
So you can say that the solution is going to be an extremal point.
Yes,
well,
but there are many of them.
There are many of them, but intuitively tells you that the solution should be expected to be a permutation, or in continuous should be, they should exist, I would say, a Monge map. So I think it's pointing in the direction. If you know about optimal transport, the most famous theorem of optimal transport is called Brognié's theorems, that tell you that under some regularity assumption, the solution is actually given by a bijection, a Brognier map. So I think this is pointing toward the fact that this should still be true. But to be honest, it's still resisting proof. Then the other thing that you've said is it's bilinear. So so you can do relaxation. So basically a standard, and it's basically how you derive the algorithm. You can do relaxation by basically minimizing alternatively on this and on this. It's actually a famous relaxation on quadratic programming. I think it's often known as Kono's relaxation, but it has many names. And you can show that this relaxation is tight. So, which means that if there are solutions, it should be solution where if you call this P and Q, P should be equal to Q. Another way to say this is that it's linked to difference of convex programming. You can also say that at least if the function is concave, sorry, you can also say that it's a difference of concave function. And you can really see that these algorithms are basically classical algorithms from DC programming. This being said, it could still be trapped in local minimum, but in practice, I think this explains a bit why it works quite nicely. So this is basically the only thing I can tell you, but yeah, you're right, it's not an arbitrary non-convex problem. And you should expect that in some case, like Euclidean space, and maybe with not too complicated input distribution, there should not be so many local minimizer, and maybe in some case the problem is not NP-hard. Maybe. But well, I don't know. But everybody's welcome to join the club. It's what's nice about optimal transport is it connects so many areas together, like basically here, for instance, quadratic optimization, but also probability, also I would say partial differential equation, because there are also like some methods that are based on partial differential equation that everybody can try his method, and sometimes like combining methods leads to super nice results.
Thank you.
Thank you, Manuel, and thank you, Gabriel. So I think we close now this session for today. Again, thank you very much, Gabriel, for your great presentation. And for the public, remember that there is no seminar next week because there will be the Informs conference. So we are back in 2 weeks from now, and we will have Fabio Shun from Italy presenting to us. Thank you very much, and see you in 2 weeks.
Bye-bye, everybody.
Thank you, Gabriel.
Thank you, Dolores, for the invitation. See you.